Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNIA presentation. Today's presentation is on the topic of applications and taking advantage of persistent memory. Now, before I introduce our speaker for today, I'd just like to do the steward on the flight bit. I'm going to point out where the emergency exits are, the buttons that you can press, and the strip lighting along the floor should be crashing down. So, in front of you, you've got an interface to the screen. There's a couple of things you can do here. The first thing you can do is you can make it as large as your entire screen should you need to see any of the details. Some of the slides are quite detailed, and viewing it through a little letterbox can sometimes get a bit frustrating. That's the first thing. The second thing you can do is you can actually ask us questions. There's a question button you can press, and we'd welcome questions today. We're going to take them at the end rather than take them during the presentation. We'll take them at the end of the presentation, so feel free to ask your questions. And if we don't have enough time at the end of the presentation to answer them all, I'll be leaving you with a link to a blog where we will put up the answers to those questions over the next few days. So your question will get answered one way or another. And thirdly, the thing that we would really like you to do today as you're leaving this presentation is to rate it. And the rating scale is pretty simple. It's 1 to 5. 1 is, gosh, I wish I'd gone and done something else. And 5 is, this is great, I could do more of it, please. And any comments that you have, we'd be grateful to take too, because they're important as we try and develop our future education and deliver this stuff to you. We need to understand what it is that you like and that you don't like about the education material we're presenting here. So today, let's move on to the speaker. Hello, Raghu.
Hi, Alex. How are you doing?
I'm very well. Yourself?
Very good.
Good. So Raghu's today's speaker, and Raghu Kulkarni joins us from Viking Technology. I'm Alex McDonald. I'm the SNIA SSSI, that's the Solid State Storage Initiative, a lot of S's there, co-chair, and I'm from NetApp. Today's presentation is going to be on the subject of these new technologies, persistent memory and applications. But before we start, just a very quick legal notice. This legal notice basically says the copyright to this material is held by SNIA. We'd like you to honor that, please. And secondly, if anything that you do as a result of this presentation causes whatever it is you're doing to break into 2 pieces, both of them are yours. Now, we're not responsible for what happens. SNIA itself is an organization, as many of you will know, of about 170 industry-leading organizations and 3,500 active contributing members. So we're a pretty active organization in terms of providing education and standards and various other pieces of work that we'll discuss at the back end of this presentation to the industry at large. And we've got about 50,000 people on our mailing list, of whom you are some of the select few that today come along to listen to this presentation. So today, Raghu is going to take us through a number of topics. And as is always appropriate, we're going to do a background, a little introduction to persistent memory, what it's about. And then Raghu's going to take us through some persistent memory applications. What's this new persistent memory technology good for? And what should we be thinking about as we perhaps come across it in the marketplace or we're developing it for it? What are the kind of applications that it's ideally suited for? And then lastly, we'll wrap up at the end, and we'll talk a little about how SNIA is involved with persistent memory and some of the links and website addresses that we have where you can get further information about not only today's presentation and not only about persistent memory, but SNIA in general. So without further ado, I'm going to hand over to Raghu. Raghu, the interface is all yours.
Thank you, Alex. Hello, everybody. Welcome to the Bright Talk. Thanks for attending this. My name is Raghu Kulkarni. I'm responsible for persistent memory at Viking Technology. Today I'm going to be talking on behalf of SNIA, and we're going to learn something about persistent memory, how it is going to get used, what are the applications, how the ecosystem is already developed, and how you can leverage this new technology. So as most of you are aware, the hierarchy for the memory and the storage has been, starting from the CPU, the access goes down from registers, caches, then there is DRAM, and all the way to the NAND flash, and there is the spinning media, which has been there for several decades now. But as you see over here, right, the latency is an important factor over here. The closer you get to the CPU, the better latency, and if you go farther away, there is going to be a higher latency. What you've been so far used to is, like, a DRAM is considered volatile, right? Your system memory is essentially DRAM, the DDR3, DDR4 DIMMs that you've been used to. So those are volatile, but there are so many different applications that could have been like thinking, hey, I need to store a lot of the data, a lot of the information, metadata in the DRAM, but I want it to be persistent. So I need the latency and also want it to be persistent. And there was not a good solution up until, in the last 5 to 6 years. There has been several products in the market that has been actually meeting that requirement. So I'm going to be talking about the persistent memory, which is non-volatile memory, how it is in the market today, what is the state of that, and how you can leverage it. So the goal for persistent memory is essentially, like I was mentioning, to accelerate, the applications has to take advantage of the lower latency that is kind of going to be very close to the DRAM speeds. And what it does is it will accelerate a lot of the applications, just by either storing the metadata or even the actual data over there. And that is going to become a game changer because it's going to change the computer architecture itself, how you've been used to thinking of programming in a way that, my data that is going to be stored in the DRAM is volatile. Now you will be changing it, and you will be making changes in the OS and your application layers that, hey, I have, essentially a DRAM speed kind of memory, but it is persistent, so I don't actually have to rebuild something when there is a power loss, when the system comes back up. It is already available in the memory. So those are some of the architectural changes that has to go around. I'm going to talk more about that in the following slides. So here, what I'm showing is, the spinning media, that is the hard drive, and going all the way to SATA SSD and an NVMe SSD and persistent memory. So if you look over here, the latency on spinning media is very high, because you are going to be reading as a block device from this, and also it is a spinning media. The NAND-based products actually did make a difference, but again, it is not going to be accessing directly. It has to go through several of the OS layers, right? I mean, there is going to be drivers from the OS, and then there is going to be some of the layers in the kernel that needs to be traversed to fetch the I/O, the data, from the backend, which is the SATA SSD and an NVMe SSD. But in case of a persistent memory, you can access it as a load store, just like how you would access, the standard system memory. So here you can see the latency is less than 100 nanoseconds typically. So you can see a huge difference between nanoseconds and microseconds access for SSDs. Right, so like I was saying, there is a convergence in the last 5 to 6 years. We have seen, the DRAM or the memory and storage kind of converging. What it means is you are trying to create a higher capacity persistent memory and kind of aligning to a lower latency as well. So that is kind of the convergence, because typically an SSD or spinning media had the capacity, but it was lacking in the latency. DRAM had the greatest and the best latency, but the capacity was not there. So there are technologies that are converging in the middle, where it tries to provide best of both the worlds. And you can see some of the products like NVDIMMs, MRAM, 3D XPoint from Intel. These are all the newer technologies that kind of fit into the middle, where it tries to provide both benefits. All right, so talking about emerging technologies, like I mentioned, 3D XPoint from Intel is one of those, where it tries to, meet the latency requirement and also the capacity. Along with that, there are other technologies coming out. Phase change memory, several companies are working on that. MRAM, there is already a commercially shipping product based on MRAM. But the capacities are not up there. There are smaller quantity capacities of MRAM-based products available in the market. And there is a newer, it's fairly new, it's the carbon nanotube-based memory that has not hit the market, but it is in the works. So the takeaway is there's going to be a lot of changes coming in the future for the media itself, like the non-volatile media, which can actually take advantage of the newer ecosystem that we are building based on NVDIMMs and 3D XPoint that's available today. So just to give you visual, view of how each of this technology compares against each other. So you can see FRAM, then there is MRAM, ReRAM, resistive RAM, phase change memory, the 3D XPoint, then the NRAM, that's the carbon nanotube RAM, and finally the NVDIMM-N. So everything that you see here in the column up until NVDIMM-N, these are, the memory technologies and the media by itself. But the NVDIMM-N, it is basically a product wherein it combines both, the SSD today, what's available, like a flash and a DRAM, both being on the same module itself. I'll go deeper into that. But here it compares the endurance, the writes, the read latencies, and write latencies. Since NVDIMM-N, you're not directly writing to the flash, the front end, the interface that's available to the applications will still be like a DRAM, as if it's talking to a DRAM. So you can see the latencies are so low, meaning you're getting the best latency for any of the persistent memory products that's available in the market today. But the capacities on this is fairly good. The highest capacity of NVDIMM-N that's available is 32 gig today. All of these products that other products here are not in the market except for the 3D XPoint memory form factor. It is coming out. We have heard in the news that there are several companies that has been using, and Intel is sampling them. So we're going to go more details into it in further slides. This is another slide where, we're talking about trying to drive home the point that, on the right-hand side, you can see the hard disk drive, and then in the middle, you can see the SSD product, and at the foremost left, you can see the persistent memory products. What happens here, what we're depicting here is the access time is getting lower, but the cost is going up, meaning the hard drive, the access time is somewhere in the milliseconds, the SSD microseconds, but the cost is not that high relative to the persistent memory products. NVDIMM-N and NVDIMM-P that is coming out in the future, and other persistent memory technologies I'm talking about, is going to be a little more expensive compared to our traditional SSDs and hard drives. All right, so that was, a basic introduction to persistent memory, where we are, what's happening in the market today. So today, what I'm going to do is deep dive into some of the NVDIMM-N product. NVDIMM-N is currently available in the market, and you can buy one of those today. The -N is basically a combination of a DRAM and a flash. Essentially, on the left-hand side, you can see the DRAM is like front-facing to the applications, so you can plug it into a standard DDR4 slot. It shows up as a persistent memory to the operating system. I'll tell you how all these things are achieved later. But there is also a flash component in this. So what happens is every time you're in a mission mode, like you're writing to the NVDIMM-N, all the data will be stored in the DRAM portion of this product. And when there is a power failure or a catastrophic event that happens, the data from the DRAM will be moved to the flash on the board, wherein the backup energy is provided by a supercapacitor that is connected to that. So the holdup or the backup energy is provided by a supercap that is attached to this NVDIMM-N, and the data from the DRAM gets copied over to the flash, and it is stored there. When the power comes back up again, the data is moved back from the backend, the non-volatile memory, which is flash in this case, gets copied back to the DRAM, and when the OS boots up and the application tries to access this, the data is already there. It kind of feels to the application that the data never went away. It was already present in the DRAM when you access it. So this provides a continuous or a data that is required by the applications at all points of time, and you don't lose any data that is stored in this portion of the memory that's mapped to the NVDIMM. There is another variant of this NVDIMM, NVDIMM-P. It is still in the standards right now. We do not have finalized standards for NVDIMM-P, but NVDIMM-P is traditionally what's going to happen is there is going to be a DRAM and a flash, just like NVDIMM-N, but you're going to have a bigger capacity of flash, and in this case, both the DRAM and the flash will be exposed to the operating system. In the NVDIMM-N, only DRAM was getting exposed to the OS. The flash that is in the back end would not get exposed to the OS. But in -P, both will be available to the OS to be used. Here, NVDIMM-P traditionally can be used both as byte addressable and block. So the standards are still in the works. You will hear more in the coming months. Stay tuned. If you're part of the JEDEC, you are already aware of this. And SNIA will be providing more updates on this as well. So here is how NVDIMM-N works today. Like I mentioned, the data will be stored in the DRAM portion of the NVDIMM, and the super cap attached to that will be charging while the system is in the operation. And when there is a power failure, what happens is the data gets moved from DRAM to the flash, and the backup energy is going to be provided by the super cap that is fully charged. You can also be monitoring the health of the super cap and also the NVDIMM through the applications, APIs, and other interfaces that's available from the OS. Move on to the next slide. So here, like I mentioned before, there is a way to access NVDIMM from the OS today that's natively supported on several of the operating systems. I'm kind of going to go deeper into that, but here you can see there are several modes of access to the NVDIMM. One is, like either from Windows or Linux, right? I mean, traditionally, you can use it as a block device if you want to make sure that your applications don't have to change, but it can readily take advantage of an NVDIMM sitting on the DDR bus. You can do that, but that's not, like taking full advantage of that. If you're using a later kernel like 4.10, 4.8, it already has a PM-aware file system built into it, so you can actually create, like a partition based on the PM-aware file system, and you would be able to access it. That is kind of the fastest way of accessing it without modifying any of your applications for the block. But the best part of that is there is also a load store way of accessing it, which is enabled in the later kernels. It's available both in Windows and Linux, so you can do a direct load store to the NVDIMM. And that's like, you're accessing the fastest way, like how you're accessing the system memory, but is also persistent. There are several open source library available. You can actually go to pmem.io. You will have quite a bit of libraries that has been developed just for persistent memory, and you can actually take advantage of it. It's already built. It's kind of tested to an extent where the interface is working. You can customize it. It's open source. You can use it however you would like to suit your applications, but there is infrastructure already built into for the libraries to take advantage of the persistent memory. So how is it different from your standard DDR4 DIMM when you plug it into the platform, right? Because you're going to be plugging it into a same DDR4 slot. How does the BIOS differentiate? Essentially, the BIOS that's coming out from Intel, it has been modified to detect this, persistent memory, NVDIMMs. Once it reads the SPD essentially to figure out what kind of DIMM is it. Once it figures out it is an NVDIMM, what it does is it puts it in a different bucket and RDIMM in a different bucket. So essentially there's going to be two different pools of memory that's created, and then it exports that information all the way up to the operating system through the ACPI tables and other firmware tables that's already built in. And what happens is in the BIOS you need to ARM the NVDIMM. We're talking strictly about the NVDIMM-N. You need to go and ARM it. Essentially, if you don't ARM the NVDIMM, then it is not going to save the data when you kill the power. So you have to explicitly turn on the arming in the BIOS. And once it is enabled, then you would be able to save and restore. Restore is another option that needs to be turned on. So BIOS is pretty easy. There are a couple options that you need to turn on. And all of the access for monitoring to the NVDIMM happens through the BIOS. And of course, that is enabled by default. This is exactly the screen that you can see over here, where in most systems, it is kind of the pretty standard menu options. So you would go and then enable these options in the BIOS. All right, so here I was talking about the kernel support a little earlier. SNIA, has a technical work group. It works with several of the companies that's part of the SNIA. And with the support of SNIA, there is an ecosystem that's available today, especially for, specifically for PMAM that Windows and Linux have leveraged. Essentially, it provides, like I was saying, the DAX is the direct access method, wherein, you would be able to access the NVDIMM's persistent memory region directly without actually having to go through, multiple blocks of I/O layers. There is also a PMAM-aware file system in this. You can access it in the block mode as well if you would like to. And like I was saying, if you go to the pmam.io, there is also several libraries, for the block translation layer and things like that. There is already built-in applications that you can take advantage of that. But you have to make sure on Linux it is 4.4 plus kernel. Older kernels do not support PMAM. You need to be on one of the later kernel versions. Both Windows 2016 server and Linux supports this. Currently, those are the two OSs. I haven't seen any other OSs in the market that support it, but any OS, if you're developing PMAM, the basic underlying is an open source, the PMAM architecture. You can actually port it to your OS if you would like to. And you can see here there is DAX access in the block, and you can see the latency difference between accessing it in block mode versus direct attached. So here is a performance graph. This is all with NVDIMMs. The first three columns are NVDIMMs. The last one is the Optane 3D Crosspoint SSD from Intel. Both are being using the file systems that's available, PMAM-aware file system. And it's the later kernel. It's basically run on Ubuntu 4.10 kernel. And you can see the difference in the performance and the latencies. The second column you're seeing is with using 4 NVDIMMs, and you can get all the way up to 5 million IOPS. And again, this is accessing it in a DAX mode. And if you compare that to an SSD, of course, it is the fastest, probably one of the fastest SSDs available today, which is a 560K. It's like a 500,000. And here with the NVDIMMs, you can get all the way up to 5.5 million. So there's a huge difference. And also the latencies, you can see it is phenomenally great with the NVDIMMs. From huge magnitude of 29 nanoseconds. Here it's actually microseconds compared to 1.3 nanoseconds. So it's pretty fast. So how can you take advantage of this, and what does it do to your applications? NVDIMM-Ns, first of all, are byte addressable. What it means is, you can access it just like, how you're used to accessing your standard system memory. You can do load stores to that. This essentially means faster access to the persistent storage. You can, use it since, the NVDIMMs are not large capacities. You can have, multiple of 32 gigs, and then you can kind of get all the way up to, 256 gigabyte, or in some cases, a little more than that, depending on how many you have per system. But what it primarily uses is for, like, enhancing your the speeds of the metadata. You're actually accelerating it. So it's a perfect metadata accelerator. Then you can typically load all your memcache structure into that, and you will be accessing it at blazing speed, as opposed to going and accessing it from an SSD using a block mode access. Here's a little number on how fast NVDIMMs are. It provides 32 times the number of IOPS compared to a standard SSD, and it is 16 times the bandwidth and 81 times lower latency. Those numbers speak for themselves, right? I mean, how fast the access rate is compared to an SSD that's available in the market. And a lot of your applications can take advantage of this as is, if needed, in the block mode also, but the performance numbers can be phenomenal, like you see over here in the load store, using the latest persistent memory aware file system in DAX mode. So that's NVDIMM-N, what is available in the market today as a true persistent memory product. So let's talk about how you can take advantage of this product to accelerate your applications, and what are some of those applications that you can use this persistent memory for. In-memory databases, right? I mean, there has been several in-memory databases that's popped up in the last several years. There have been offering from Oracle to Microsoft to MySQL, and there are like SAP HANA. There are several in-memory databases that's coming out, and one of the and also it can be used with the traditional databases. But in all these databases, essentially, metadata is also a very important factor. So for factors like journaling and keeping the read logs, and also managing and maintaining a lot of the tables, you would be needing frequent access to this. And if you are going to the SSDs for every one of these transactions, it is going to prove very expensive, and it may not be efficient from a latency perspective. So you can park all of that information in the NVDIMMs or persistent memory, wherein the accesses are going to be blazing speed. You cannot really load the entire data sets into the NVDIMMs because NVDIMM capacities are small. So NVDIMM-Ns are a perfect product for storing all the metadatas. In the other product that we are going to talk about, the 3D Crosspoint Optane DIMM, that is kind of available in the market. It's trickling down slowly. Those would be perfectly suited for both metadata, as well as you might be able to load some data sets on it depending on how big it is for you. The other use case for NVDIMM-N is an enterprise storage arrays. Essentially, it can be any of your HCI or any storage platform. It is going to be used for, basically caching, right, buffering or tiering, right? All the IOs that comes in, it would be a perfect area for you to park that IO. It's like a landing zone, and you acknowledge to the requester that, hey, I've received the IO. So this is a perfect caching or buffering device. Traditionally, the RAID systems in the past were using battery-backed DIMMs. There are a lot of disadvantages with that. NVDIMM is a true replacement for that technology. In high-performance computing, this product also finds very compelling, space because, for the checkpoint of checkpointing, all of those high-performance computing usually fetches the data from several nodes, and at some point of time, it does take a snapshot or checkpoints, and you need those checkpoints, and NVDIMMs would be a perfect place for you to do those, because if you are going to lose one of those checkpoints, or if you don't achieve checkpoint at the specified time, there is going to be a huge penalty on your computing time on the HCI, on the high performance computing environments. So like we talked about, in-memory databases, traditional databases, and it can also be used as a perfect cache for the enterprise storage. This actually improves the productivity in your entire overall system effectiveness. Here's an example of an OLTP and an OLAP kind of environment, right? I mean, so with DRAM or without persistent memory in the picture, traditionally, you would be keeping all your hot data in the DRAM, and a warm data, like less frequently used, but it's not like a really cold data. Those would be in your warm tier, typically an SSD, and your cold data, which is kind of very infrequently used, would be in a SATA SSDs. But with the new persistent memory technology, what you can do is combine both the hot and the warm data in the persistent memory itself, so that you don't actually have to create two tiers. You will be having an access to both data at all times with a low latency. So you don't actually have to do tiering over here from a hot and warm perspective. You can have a higher capacity and a lower latency. So this is going to be a huge advantage for these environments, wherein you can service your data much quickly, because OLTP is an environment where online transactions happens, and you need an acknowledgement right away, and this would be a perfect use case for that. So here is a couple more segments and applications that can take advantage of persistent memory. I've touched upon a couple things in the past, but here you can see in the first column talking about the databases that can take advantage of persistent memory. The scale-out storage, VMware is coming out, or actually it is supporting NVDIMM-Ns today. So you would be able to take advantage of this natively supported by VMware. And, you can do everything that you can do with the vSAN, with as if you were to be using an SSD. NVDIMMs can be natively supported in vSAN environments, so that, you can carve out the persistent memory regions for each VMs and for all other operations that's possible with the VMware that is actually a huge improvement and a huge advantage to the data centers. Of course, with the VDI, it is also available. VDI is, again, today, without the persistent memory, there were several disadvantages. It had to live with using the volatile system memory. Now that you have persistent memory, it is hugely advantageous to these applications. Big data, all the MongoDB, the Hardenbergs, Hadoop, all these things, applications can take advantage of persistent memory, especially for the metadata, because, there is going to be a lot of data crunching, and you would need a bigger metadata, because as the data sets and data size grows, the metadata also kind of grows, and then you would need the access. You would need access to these metadata at a lower latency, and NVDIMMs are a perfect product for this. We talked about in-memory databases. Then there is support for Java and .NET coming as well. There are some libraries available in the pmm.io. There's more work on a way, essentially, to be able to use, the persistent memory directly from Java and .NET. That would be huge for all the software developers, application developers, where you can actually access this memory directly. And this is going to be another game-changing effect. We talked about HPC, high-performance computing environment, how it is going to be useful. So that kind of, was some of the applications that you can take advantage of persistent memory. Here is, a little hierarchy of how, traditional storage is set up today. The access, if you were to say, hey, from application, if I'm going to talk to an SSD, this is like, your typical stack, layered application file system, the device driver and the medium. But with, there's, you can go to the next step, which is the Horizon one over here, and then go to the second one. Today is where we are, like Horizon 2. The application talks to the PM library, and PM library talks to either file system to expose it as a DAX file system aware device, or you can do load store directly to persistent memory. So this is where we are today. But the end goal is going into Horizon 3, where the compilers are going to be able to access the persistent memory natively, like, it's built into the compiler, like how you were to be doing like a malloc or something like that. This is exactly the slide talking about how you would be taking advantage of this directly from the application, wherein it's built into the compiler itself. All right. Here we're talking about the two persistent memory products that's kind of available in the market. NVDIMM-N, it is available. You can buy it today. It has been shipping from several years. It's a proven technology. There are platforms, the entire ecosystem built for this. 3 cross-point Optane DIMMs. It is very new in the market. The -N, like I mentioned, it is useful for metadata acceleration, and also for the storage, where you can use it as cache. The 3 cross-point Optane DIMMs are typically going to be used for in-memory databases, or even for some of the traditional databases, depending on the data sets. Because these have higher capacities, you can load the whole thing into this persistent memory. So there might be some questions around, hey, is one technology going to replace another, or 3D cross-point Optane DIMM is going to replace NVDIMM? No, they both are persistent memories addressing different applications. They both can coexist. They are geared towards different applications. One NVDIMM-N is going to be centered around low latency and a lower capacity kind of applications. Cross-point Optane DIMMs are going to be a little higher latency but higher capacity. So the two different use cases and applications. Here are some examples. I'm going to run through this. This is actually a real customer using NVDIMM's persistent memory to accelerate their solution. DreamWorks. They have 600 terabytes of data on one film. And there is going to be a lot of access to this, small, tiny amounts of data at periodic amounts of time. And with the NVDIMMs, they were able to solve some of the latency issues. I'm going to answer some of those questions about this later in the blogs. So another use case for this is the HCI. We have some customers in the HCI, the hyperconverged infrastructure environment, where they're going to be using the NVDIMMs for providing low latency, like I was talking about, providing the metadata for dedupe, and you can even store a lot of your real data in there as well, but it provides a huge benefit from a metadata perspective in this environment. And there is another example, like where WDC, the Western Digital guys, Tegile, now a part of WD, is using it traditionally for enterprise storage, wherein you're going to receive the IOs in the persistent memory, and you acknowledge right away to the OS or to the requester. So this is going to give you higher IOPS and a better serviceability to the applications. Here we're talking about workloads. This is a real example. You will be like you can see here with NVDIMMs and without NVDIMMs on two different workloads. The first one is 80-20 read-write workload, and the second one on the right-hand side is 50-50 read-write workloads. You can see how the latencies are going to be improved with the use of NVDIMM in the solution. The blue line that you see is without NVDIMMs, and the one at the bottom, you can see how adding NVDIMMs or persistent memory, improves the latency of the overall product. Infrastructure changes, all of these things, enabling persistent memory was, a lot of work with several teams and several standard bodies and several companies coming together and making sure that the ecosystem is built. It was not like, a turnkey product or a technology that, you build it in and say, hey, send it, provide it to the customer and say you can use it. It's not like it was not available. The ecosystem had to be built organically from ground up. Operating system is developed now, at least from Linux and Windows perspective. They support natively NVDIMMs. So OS is ready. There has been file system changes. Several file systems, we're talking about the VMware Avail file system, is available now to take advantage of the persistent memory to provide lower latencies. There are several management software available along with this OS. There are libraries available that you can use to manage and monitor the NVDIMMs, the supercaps, any other persistent memory products as well. Hypervisors and containers are also changing. Like I was talking about, VMware has added support to it. It's a huge advantage. If you guys are in the VMware environment, please check it out. And also, a lot of the libraries are getting built up. There are libraries available in pmem.io that you can take advantage of it readily. That's available. So, like I mentioned before, it required several of the standard bodies to come together. SNIA, along with JEDEC and the ACPI standards, working in tandem, has brought this technology to the market from the ecosystem perspective. SNIA and JEDEC have played a big role with ACPI coming in to provide an interface to the OS to monitor the NVDIMM. So there has been a lot of work. If you are part of JEDEC, check out the JEDEC 245 space. SNIA, persistent memory groups. You should also, take a look at the SNIA's contribution to this. And one thing did not touch before is encryption. A lot of the NVDIMMs that's available in the market today also support encryption because NVDIMMs are kind of memory devices, but at the same time, the data is going to be stored. It's persistent. So several products that's available today, NVDIMM-N, do support encryption. So, the key takeaways from this presentation is, the NVDIMMs is the first step. NVDIMM-N is the first step to the persistent memory, and it's here today. You can take advantage of it. The product is available in the market, and the ecosystem is built up. So take advantage of this. If there are any questions, you can reach out to SNIA, and we can address this as a part of SNIA. Any of the questions you might have, or you can even contact the individual companies that you're going to be working with on this product. But SNIA has the forefront in this, and we can help you answer your questions to implement persistent memory in your solution. Like I briefly mentioned, there are a couple technical work groups within SNIA, and there are a lot of activities and events going on. It is actively driving the standards, even for the future memory technologies. So take a look at it and then participate. If you have any questions, feel free to ping the SNIA group. And this is the JEDEC that I was talking about before. You can participate and be part of this JEDEC committee as well. And with that, I will turn it over to Alex. And Alex?
Thank you, Raghu. So I hope my audio is still holding up. There's somebody on my street consumed huge amounts of bandwidth, and I think I'm coming with an IP connection here. So apologies if it's a bit choppy. It should be okay, though. So we've probably got a few minutes for some questions. So let me see if I can just pick up on some of these questions I asked. One that's really interesting here, Raghu, should persistent memory usage be compared against storage or memory? Is it more storage-like, or is it more memory-like? What's the, what is the use case drivers towards?
So, like I was saying, it depends on the application, right? I mean, it is primarily a memory device, okay? For all intents and purposes, you would be treating that as memory device because it's byte addressable. Because if you're thinking of it as a storage device, then there are other storage products available in the market. But since the fact that it's sitting on the DDR bus, you would be taking advantage of the lower latency, and there are multiple applications that will do it because the data is still persistent, but it's not like, a huge data that's available. Like, you're not going to treat that as a permanent storage for multiple data sets. It is essentially, like I said, perfect use case for metadata. You want it to be persistent, but you want a faster access.
Okay, thank you. So I know we've got a number of other questions. We're going to answer those on the blog site, and the blog site I'll show you that as we go through it. But basically, I'd like to thank you for coming along today. There is actually something, for those of you who are based in the Santa Clara in California area, there's a Persistent Memory Summit that we run every year, and this year it's on January the 24th in Santa Clara. And you'll see on SNIA.org TM-Summit, there's a full agenda of persistent memory topics, a lot of which will be covered that day and will be available afterwards as well. One of the things that we do with this information and these educational pieces that we do is put them up on the website. So you will see that. But if you want to be there in person, January the 24th, PM Summit, you can register today and secure your place. The other thing that we're doing, and this is quite interesting because this is the first time that this has happened. Many of you may be aware that one of the ways that vendors test their equipment is by testing against each other's equipment software. So there have been for a number of years hackathons to do with, for instance, NFS as a file protocol, or SMB, Microsoft's SMB protocol. And these hackathons are pretty popular in that people get together in the same location and try and make sure that their products will interoperate and cooperate with each other, and that they're all meeting the same parts of the standard in the same way. We're having a hackathon this year on January the 23rd, so there's going to be a persistent memory hackathon. I'm not quite sure what this is going to look like, but as I'm going to be there, I think I might just drop in and find out how they actually do a persistent memory hackathon. But there's also a complimentary registration there if you have a persistent memory solution that you want to test against other people's applications, you can do so. So thank you very much for attending. That's the blog address, SNIA-blog.org, where we will put up the Q&A to this. We will also put up on the SNIA.org/SSSI part of the website this presentation, and you'll get an email telling you where the presentations can be found. It may already be up. I'm not quite sure that we've got it up yet or not, but it may already be up, this presentation. One thing I would recommend that you do when you look at the presentation that struck me today when we're going through the slides, I'd like you to look very carefully at those graphs. Those graphs are not linear. They are logarithmic. Persistent memory is literally thousands of times faster than SSDs, which are literally thousands of times faster than traditional hard drives. So this is a step-changing technology. This is something where, we're approaching 1 million times faster than a hard drive for persistent memory, yet still with that persistent characteristic. So when you go back and look at all those graphs, just bear that in mind. Just bear in mind that these are logarithmic, and the differences that you're seeing are quite staggeringly huge. Anyway, today I'd like to thank you for coming along to this presentation. I'd like to thank Raghu for his very entertaining and interesting information that he's given us. Your last favor to me is as feedback. I need feedback for this. I'd like you to, as you lead the presentation, to actually score us on a 1 to 5. Remember, 1 was goodness, should have been doing something else. 5, great, give me more of this. And any comments that you may have that allow us to improve our presentation. But in the meanwhile, thank you very much for attending, and have a good rest of your day. Thank you.